Welcome student. PCH 280151 unit for reaction mechanism, in which after discussing ET reaction in lecture 3 we will going to discuss outer sphere ET reaction mechanism. There are so many conditions for the outer sphere ET reaction mechanism to be proceed. I am Dr. Devanga Pandya from Department of Chemistry, St. Javiers College, Autonomous, Ahmedabad. Well, point to discuss in today's this one lecture. We will start with the introduction to the mechanism of redox reactions and outer sphere reaction. So already we have discussed, defined the outer sphere mechanism, but here we are going to discuss that with certain different examples as well. Then we're going to discuss the mechanism of outer sphere redox reaction, and these 2 points we're going to discuss in this lecture. Let's begin with introduction to the mechanism of redox reaction and outer sphere reaction. The metal complexes which do not go through substitution reaction involves outer sphere electron transfer reaction. So in outer sphere there is no substitution. That means there is no role of the spectator ligand in it. The spectator ligand should remain inert, or the outer or the sphere of the complex, both reactive complex or redox couple, should remain inert in this reaction. Only electron will transfer. It means none of the bonds are broken or formed in either of the metal complexes or metal reactants or redox couple, whatever word you can use, you may. In other words, these reactions include complementary change in the oxidation state of both the metals through a pathway where the ligand does not undergo breezing mode in the coordination sphere of complexes. Unlike in a sphere mechanism, here the outer sphere of what the redox couple, or we can say reactant complexes, remain unaltered during the reaction. Therefore, coordination sphere of the metal complex reactants in an outer sphere reaction stay intact. There is no change whatsoever, which already I have said earlier. The favorable factor for an outer sphere reaction is the inertness of the complexes towards substitution over the time needed for a redox reaction to occur. So these conditions should be there, that the outer sphere of each complex participating in redox reaction must be inert, and in this inertness of complexes, substitution over the time needed for a redox reaction to occur. So instead of substitution, only electron transfer may take place through Frank-Cordon principle, that the velocity of electron is greater than that of the nucleus. Here the example, common example, this one is the oxidant, you can see over here, and this one is going to be the reductant. So oxidant get reduced and reductant get oxidized. Example of outer sphere reaction. Here very simple example which already we have given in the previous lecture, much in the same way it is there over here. Fe hexacyanoferrous complex is there and hexachloroiridium complex is there, and both this outer sphere remain inert. Then the electron transfer will take place from ferrous to iridium. So ferrous converted into ferric, and iridium from +4 oxidation state convert to +3 oxidation state. So that way redox couple take place over here. This is another example where you can see dimethyl bispiridine tribipyridine complex would be there, treating with tribipyrimidine. That means here substituted bipyrimidine there, and here non-substituted bipyrimidine there, and there also the outer sphere remain intact, inert, and the electron transfer take place between these two ion centers, and we're going to get this rate constant for the reaction. These reactions are genuinely quite fast, and before Lx or Ly exchange or ligand spectator ligand exchange or any bridging take place, the redox process take place rapidly. So the electron transfer rate is quite faster compared to the nucleus or any other ligand substitution reaction. Hence, it will follow the Frank-Codon principle as well. The coordination sphere of the complex remains intact because reactants do not interact significantly with each other during the electron transfer. As for example, we can say through the space diffusion control, these things may take place. Here, oxidant is there, lose the electron, a reductant will gain the electron. The example of such behavior are self-exchange, auto-exchange, electron transfer reaction. So sometime outer sphere reaction is also abbreviated or named as self-exchange reaction or auto-exchange electron transfer reaction or self-exchange electron transfer reaction between homonuclear complexes. That means if the complex having similar metal center and inert spheres may undergo this kind of self-exchange electron transfer reaction mechanism. This is the example for that. Ligands are similar, metal center are similar, homogeneous, and as a result of that the electron transfer may take place. So here you can see the first complex, which is +2, lose the electron, turns +3. This one +3 oxidation state, gain the electron, turns +2. The outer sphere rates for self-exchange reactions are this one. This tabular will going to show you how much rate of reaction would be there. These are different metal Fe, and these are certain ligands, and here the spin of the state of D configuration of electron, low spin complex, and you can see rate is quite greater than 10⁻⁶. And if Fe is there, H2 ligand would be there, high spin complex of D5 D6 would be there, and you can see this is the rate of a reaction. So that way you can compare the rate of reaction of this D5 D6 D7 complexes, high spin or low spin complexes, with these different ligands associated with it, and there should be certain parameters which are going to affect the self exchange electron transfer reaction mechanism as well. The representative example of self-exchange electron transfer reaction is, these are the example. Here you can see ruthenium hexamine complex, both the side. This one is put a start over here, so that is it is a radioactive element of this metal center. You can see both complexes are similar. One is simple ruthenium, other is radioactive element, and you can see the electron transfer take place. +2 is converted into +3 and +3 converted into +2. So electron transfer from this one to this one, and the rate constant would be 8.2 into 10⁻²⁰ meter inverse second inverse. And here you can see the electron potential would be 0.051 volt, wherein the ruthenium and ruthenium star are isotope of each other, and delta G0 is going to be 0. The other simpler self-exchange electron transfer reaction would be this one, where these two different metal centers are there, and yet electron transfer from cobalt to chromium, and the oxidation state of cobalt, which is +2 over here, converted into +3 over here, and +3 of chromium now converted into +2, gaining the electron, and the electropotential would be 0.058 volt. So these are the two examples of self-exchange electron transfer mechanism, which is also known as outer sphere reaction, outer sphere ET reaction. Despite odd situation and requirements for an outer sphere reaction, The lowest energy barrier, notwithstanding, can be yet presented by an outer sphere pathway. This criterion ambiguity is observed in metal aqua complexes, in which one of these is labile in terms of substitution over redox reactions time scale. For instance, we have this example. Here in this chromium hexaaqua complex and chromium hexaaqua complex, this is isotope, radioisotope of each other, and the electron transfer from this to this, plus 2 converted into plus 3 and plus 3 converted into plus 2. Rate constant would be greater than or is less than or is equal to 2.5 into 10 raised to minus 5 meter inverse second inverse. So you can understand how much rapidly the electron transfer take place in this outer sphere mechanism. For such reaction, indirect arguments may be raised for a while, as for example, outer sphere rate of reaction for oxidation of hexaaqua-chromium plus 2 complex appears to be typically 10 to 6 times lower relative to well-known outer sphere reaction involving hexaaqua-chromium plus 2 employing same oxidation state. The relative rate of self-exchange electron transfer reaction for hexaaqua chromium plus 3 and hexaaqua chromium plus 2 redox couple versus ammonium monoaqua ammonium ruthenium complex with this one plus 2 couple is fairly informative, because the higher oxidation state, that is plus 3 charge complex for each couple, is transferred to hydroxo complex. The maximum rate of self-exchange reaction for the specific chromium plus 3 to chromium plus 2 couple is 2 into 10 raised to minus 5 meter inverse semi-inverse. However, for Ru plus 3 to plus 2 redox couple, it has not been directly measured. Although rationally the specific rate of for this redox couple can be considered close to that of this, and that is 1 into 10 raised to 3 meter inverse second inverse. Now, mechanism of outer sphere reaction mechanism. The mechanism of outer sphere redox reaction initiates with the formation of a precursor complex, which further undergo rearrangement route to become suitable for electron transfer process. In these reactions, one of the reacting species utilizes the second coordination sphere or outer sphere of other reacting species. Both the reactants involved must be inert towards substitution to prefer outer sphere mechanism over that of inner sphere mechanism, and there should be absence of breaching ligand as well. Now this would be the general mechanism: oxidation concentration, redox concentration, and this is a rate constant for this A, redox obliques or oxidation oblique reduction, and this is of ET reaction electron transfer, and this is for dissociation. So K observation would be Ka into KEL or ET. In the complex form, it can be depicted as the precursor complex formation is basically that where both the reactants are weakly interacting to each other without changing their oxidation state and indeed in equilibrium. Here is the example for that. And we can see here the transition of precursor complex where the electron transfer takes place between these two. And second point, recognition of the precursor complex to become suitable for electron transfer, followed by relaxation of the successor complex. So here the relaxation of successor complex. The dissociation of successor complex eventually leads to the formation of ultimate products where both the complexes have changed their oxidation state by 1. So here you can see the successor complex, where after electron transfer take place, we're going to retain the dissociation and it will result into two different complex. So electron transfer now taken place completely in these two steps. The rate of reaction can be determined from step 2, which is the slow step of the reaction, whereas the formation of precursor complex as well as dissociation of the successor complex is quite rapid. So 3 steps among them, the second step is the rate determining step. Here you can see the thermodynamic energy profile diagram for the outer sphere reaction mechanism. Here from the lower energy gives free energy delta 0, reactants are there. Then after when these two complex interact with each other, it will going to increase the energy, gives free energy, and then when the precursor complex form, the energy dripped a little bit. Now here the electron transfer take place, and when the electron transfer take place, the energy even increases, and it increases for the electron transfer. That's why it is delta GET, and it reaches to the transition state, where the probability to be either metal electron has equal probability to enter into either metal, but it will enter from one metal to other when the energy dripped and reached to successor complex. And after the successor complex, the dissociation take place. When the dissociation take place, and again the energy increase a little bit, and then when the complete dissociation take place, we're going to get the product. So here that energy change is associated during this outer sphere ET or electron transfer reaction mechanism. Now let's sum up this all the points. The outer sphere reaction can be homoelectric or heteroelectric in nature, but whenever these are homometallic, named as exchange reactions, the complexes of ferrous to ferric or cobalt to cobalt plus 3, ruthenium plus 2 to plus 3, etc. we have discussed in here. Outer sphere reaction involves simple electron transfer without ligand sharing or bridging using Frank-Codin principle. Self-exchange reaction, that is also known as outer sphere mechanism, imparting metal complexes having same metal and ligand have been illustrated over here. Redox reaction rate must be more rapid relative to the substitution of ligand. Electron transfer process is the slowest path due to the electrostatic repulsion, and thus it is a rate determining step. Step 2 is a rate determining step, and electron transfer occurs if all the orbital of both the redox couple are of the same energy. This is enough from my side. Thank you very much for paying attention to this video lecture. Keep asking question. As you know, asking question is a beautiful way to gain knowledge. Thank you.